Hello students, in this video we are going to see the dimension of a subspace. The dimension of a subspace. Let us see one theorem. Suppose vectors b1 bar, b2 bar and so on up to bp bar span a subspace W. Span a subspace W. And let set a1 bar, b2 bar, a1 bar, a2 bar and so on up to aq bar be any set in W with q is greater than p, then set a1 bar, a2 bar and so on up to aq bar must be linearly dependent. Suppose in this theorem we have given that vectors b1 bar, b2 bar and so on up to bp bar span subspace W. Means what? Every vector in W can be written as a linear combination of b1 bar, b2 bar and so on up to bp bar. And set a1 bar, a2 bar and so on up to aq bar be any set in W with number of vectors in this set is greater than this set. Then set a1 bar, a2 bar and so on up to aq bar must be linearly dependent. Okay, let us see proof. Let b is equals to b1 bar, set b1 bar, b2 bar and so on up to bp bar, and a is equals to matrix a1 bar, a2 bar and so on up to aq bar. Since b1 bar, b2 bar and so on up to bp bar span a subspace W. Therefore, every vector in W is a linear combination of the vectors b1 bar, b2 bar and so on up to bp bar. Okay. Hence each aj bar is a linear combination because set a1 bar, a2 bar and so on up to aq bar be any set in W. That's why each aj bar is a linear combination of b1 bar and so on up to bp bar. Okay. Therefore, there exist a scalars Cj1, Cj2 and so on up to Cjp such that such that AJ bar can be written as CJ1 B1 bar plus CJ2 B2 bar plus and so on up to CJP BP bar. Okay. This can be written as matrix B1 bar, B2 bar and so on up to BP bar into matrix CJ1, CJ2 and so on up to CJP. Okay. Therefore, AJ bar is equals to, this matrix is B bar into CJ. For each J is equals to 1, 2 and so on up to Qn, where Cj is equals to, Cj is nothing but matrix Cj1, Cj2 and so on up to Cjp. Okay. Therefore, here AJ bar is equals to B bar into Cj. Our matrix A is A1 bar, A2 bar and so on up to AQ bar. Therefore, matrix A is equals to A1 bar, A2 bar and so on up to AQ bar is equals to, see here AJ bar is equals to B into CJ bar. For J runs from 1 to and so on up to Q. So here is equals to matrix A1 is equals to B into C1 bar. A2 bar is equals to, here B bar into C1. A2 bar is equals to B bar into C2 and so on up to B bar into CQ. Okay, which is equals to, this is nothing but B into C. Call this equation number 1. Where matrix C is nothing but C1 bar, C2 bar and so on up to CP bar. Clearly, matrix C is P by Q matrix. Means this C matrix contains number of rows P and Q number of columns. Now consider the equation. C into X bar is equals to 0 bar, which is a system of P equations in n unknowns. With Q is greater than P. Therefore, there exists a non-trivial solution for C into X bar is equals to 0 bar. Because C into X bar is equals to 0 bar, which is a system of P equations in n unknowns with Q is greater than P. Therefore, there exists a non-trivial solution for C into X bar is equals to 0 bar. Say U bar, that is there is non-zero vector, u bar such that c into u bar is equals to 0 bar. Suppose non-zero vector u bar is a solution of this system c into x bar is equals to 0. Now a into u bar is equals to, but a is equals to b into c. We have already seen it, into u bar, which is equals to, this can be written as b into c into u bar, but c into u bar is equals to 0 bar. So b into 0 bar, this is equals to 0 bar. Therefore we get a into u bar is equals to 0 bar, where u bar is non-zero vector, Therefore the columns of A are linearly dependent. Therefore columns of A are linearly independent. That is, set A1 bar, A2 bar and so on up to AQ bar is linearly dependent. Because a into u bar is equals to 0 bar. Here u bar is any non-zero vector. That's why the columns of A are linearly dependent. That is, the set A1 bar, A2 bar and so on up to AQ bar is linearly dependent. Hence, proof of theorem is completed. Let us take one note. The above theorem can be stated in other words, if a subspace W is spanned by vectors b1 bar, b2 bar and so on up to bp bar, then any set of vectors more than p in W is linearly dependent. Let us take next theorem. If A and B are bases, for a subspace, W of Rn, then A and B have the same number of vectors. Proof. in this theorem we have to prove if A and B are bases for a subspace W of Rn, then A and B have the same number of vectors. A and B are bases means A and B are linearly independent, and A and B spans W. Means what? Every vector in W can be written as linear combination of vectors in A and also in vectors in B. Let us see proof. Suppose there are P vectors. Suppose there are P vectors in the basis A. Okay. Basis A of W, and Q vectors in the basis B. P vectors in basis A and Q vectors in basis B. Here our claim is to show that P is equals to Q. Okay. Since A is basis for W, obviously it spans W. Okay. Hence, by previous theorem, as B is a set of vectors. B is a set of vectors in W. B is a set of vectors in W if Q is greater than P, because A contains P vectors and this B contains Q vectors. Therefore, by above theorem, Q is greater than P. Similarly, as B is basis for W, so span W, and A is set of vectors in A is set of vectors. So again by previous theorem, P is greater than Q. Okay. Because number of set of vectors in set is greater than number of vectors in basis, which is here Q is greater than P and P is greater than Q, which is possible only in P is equals to Q. Okay, therefore P is equals to Q, means A and B have the same number of vectors. Let us write down one note. For a subspace of Rn any two bases have the same number of vectors. Have the same number of vectors. Let us see definition of dimension of subspace. The dimension of a non-zero subspace, the dimension of non-zero subspace H denoted by dimension H is the number of vectors in any basis for H. The dimension of a non-zero subspace, it is denoted by dim H, is the number of vectors in any basis for H. Okay. For example, first, the set matrix 1 0, 0 1 is a standard basis for R2. We have already seen it's a standard basis for R2. Therefore, dimension of R2 is equal to 2 because this basis contains two vectors. Okay. Second, set E1 bar, E2 bar and so on up to En bar is a standard basis for Rn. This set contains n vectors. Therefore, dimension of Rn is equal to n. Third, the dimension of the zero subspace is 0 because its basis contains 0 elements. Let us write down one note. Given matrix A, to find dimension of null space of A, simply identify and count the number of free variables in A into x bar is equal to 0 bar. Dimension of null space. To find the dimension of null space of A, simply identify and count the number of free variables in a into x bar is equals to 0, 1. That is, dimension of null space of A is nothing but the number of free variables in A into x bar is equals to 0, 1. Okay. Let us take next definition, rank of a matrix. The rank of a matrix A, it is denoted by rank A and is defined to be the dimension of column space of A. Dimension of column space of A. Okay. Let us write down one note. Since the pivot column of A forms a basis for column A, comma, the rank of A is just the number of pivot columns in A. Okay. What is definition of rank A? Rank of a matrix is the dimension of column space of A. And in note we have written that the rank of A is just the number of pivot columns in A. Okay. Let us write down next theorem. The rank theorem. This theorem is also called rank nullity theorem. If a matrix A has n columns, then rank A plus dimension of null space of A, which is equals to n. Dimension of null space of A is nothing but nullity. What is theorem? If a matrix A has n columns, then rank of A plus dimension of null space of A is equals to n. Okay. Let us take next theorem, the invertible matrix theorem. Let A be n by n matrix. The following continued statements are equivalent the statement that A is an invertible matrix.